Welcome to note set number 6, where we're going to start getting into the Z-transform. So again, you've seen Z-transform in your signals and systems class, but we're going to get into some details. So this is somewhat of a review, but we'll be getting into a little bit more detail on its mechanism and its machinery, in particular talking about the region of convergence, which I purposely kind of waved my hands over in the signals and systems class. So we'll talk about that. That'll take up the majority of this note set, and then in subsequent note sets we'll talk about more applications of the Z-transform. Let me get my pen and everything set up here. You can't see that I'm doing something, but I am. Okay. Just hitting this block diagram again of this kind of roadmap of all the discrete time system relationships. This is something that I made up long ago to just kind of show in a snapshot all the different tools that we have available and how they're related. So far in this course we've already talked about the difference equation and the block diagram and the impulse response. We've not seen how to get the impulse response, but we've talked about it. We've talked about how the difference equation can be linked to a block diagram and vice versa. So by inspection, you should be able to convert back and forth between those, at least for the direct form type 2 block diagram. And in this particular set of notes, we're going to not completely talk about transfer function, but we're going to get into that. Let's see if I can get rid of these things. There we go. We're going to use start talking about the Z-transform, which is the tool that we use to talk about the transfer function. So on one hand, the transfer function is nothing more than the Z-transform of the impulse response. And also we can get the same transfer function by inspection from the difference equation. So we talked about that in the signals and systems class, but basically you look at this structure and this structure to get the respective structures of the denominator and the numerator. We'll also talk in this note set and then subsequent note sets the connection between the transfer function and the frequency response, which is nothing more than the DTFT of the impulse response. So even though we haven't really talked about the DTFT in this course, we did briefly introduce it in our review, and we will be getting into it in more detail, but I do assume that you remember that we covered that before and that you have some at least pretty good idea of what that is. So before we get into things here with the Z-transform, let's just define some things and try to get a feeling for why we're doing all this. So we're trying to develop these transforms to allow us to analyze systems as well as analyze signals in and of themselves, but we're mostly interested in how to analyze the interaction of a signal with a system. And we've already seen that in the time domain, that interaction is convolution, and convolution is very useful, but it's quite difficult to visualize and think about. And it turns out that if we go into these transform domains and use these transform tools, DTFT and Z-transform, we can get a much clearer idea of how systems work. And that helps us specify the kinds of systems that we want, as well as develop nice design methodologies for doing that. So we've got the frequency response of a system, which is nothing more than the DTFT of the impulse response, which is what I'm showing here. And we've got the Z-transform, which gives us the transfer function. So we've got the transfer function of the system, which is nothing more than the Z-transform of the impulse response. And If we're dealing with a system that has zero initial conditions, we have exactly the same result, that the output DTFT can be found from multiplying the frequency response times the DTFT of the input. And remember these superscripts that I use, that I've borrowed from Peratt's DSP book. The lowercase superscript f tells us that we're talking about DTFTs, and the superscript z tells us that we're talking about z transforms. And you can see here how that's handy. If we were to replace the omega by something, we would lose track of the fact that that's really a DTFT. We don't want to have to rely on the argument of the function, because as we get into things, we'll be doing changes of variables and things like that. So here's a question. If both the frequency response and the transfer function basically boil down to allowing us to analyze systems using multiplication, so we have multiplication in both of those two cases, why do we need both? And the answer is that really the transfer function is a generalization, and it allows us to do things and handle cases that the DTFT does not. So it's a more powerful tool. So it's like asking, well, if I have a power saw, like a circular saw, why do I need some more delicate hand saw? Well, there may be situations where the circular saw is not an appropriate tool. But there may be cases where if all you had was the hand saw, you would really want to have the circular saw, the electric circular saw. So it's just two different tools that are related. They're both saws, but one is more applicable to one scenario and the other is more applicable to another. So the transfer function provides a lot more insight into system characteristics. So if you remember from the end of the signals and systems class, the transfer function gives us the idea of poles and zeros, and that insight we can't really get from the frequency response. So this idea of poles and zeros allows us to see a lot more into the characteristic of why a system behaves the way it behaves. And so that's this greater insight part. It also allows us to handle situations where the system is unstable. So the transfer function does not exist for an unstable system, so we can't really use that tool to analyze an unstable system. Now you might say, well, if the system's unstable, why would we care about it? Well, in some situations, when we're trying to design a system, we may not know which design parameters settings will lead to stable and unstable. So we need a tool that will allow us to essentially not have the method break down if we happen to stray into an unstable setting during the design process. So the transfer function view provides us a way of not having to worry, at least when from the context of whether the math works or not, whether the system is stable or unstable. So we can work our magic during a design, and if the design ends up happening to be unstable, we'll discover that at the end and say, okay, I know that this result is valid because my tool works here, but I see that my design is unacceptable, and we'll start over. And then another thing, and this is more from a control systems point of view than a DSP point of view, although it does show up every once in a while in DSP. But the transfer function idea, and more generally the Z transform tool as a whole, allows us to analyze systems with initial conditions, whereas the DTFT viewpoint does not allow us to handle that. So now let's flip this question around. So, we just asked ourselves, if a hand saw and a circular saw both cut things, why do we need the circular saw? Well, we need the circular saw because it's a more powerful tool. and there will be times when we need that power. So now let's flip it around. If we have a circular saw, why do we need a hand saw? Well, there's going to be times when you're trying to cut a small piece of wood where a circular saw would be impractical. So similarly, not an exact analogy, but the DTFT provides us a better way to connect things back to reality, to think about how the system interacts with a signal. So the Z-transform gives us a great tool that allows us to kind of see the basic behavior and structure of a system. And then once we have that under control, no pun intended there, once we have that under our fingers, so to speak, we can then switch over into the DTFT view to see how this connects back to our view that all signals that we're interested in the real world can be thought of as being made up of a whole bunch of different sinusoids. So if you're into audio or anything like that, you may be used to thinking about a signal, some music having more bass or more treble or needing more mid-range. Those are views that come from thinking about it in terms of frequency response. So we will often see that we will first pull out the transfer function Z-transform view, do a lot of powerful analyzing of a system, and then designing. And then at the end, once our design is settled, we'll kind of flip back to the frequency response viewpoint. Once we're assured that we have a stable system, we'll flip back to the frequency response and interpret it from the point of view of how different frequencies go through that system. And the reality is that engineers think about these two things simultaneously. In fact, as we're messing around with the transfer function viewpoint, we're constantly thinking in the back of our mind about the frequency response and how the frequency response is related to that transfer function, and in particular the poles and zeros of that transfer function. Okay, talking about the Z-transform definition now. And again, I know we haven't precisely defined the DTFT other than in the very first set of notes. But again, you've seen that before, so I'm not going to fuss over it. So if we're given a DT signal, x of n, we can use this equation here to find the DTFT of that. And I'm just pointing out here to remind you that this thing is periodic 2 pi, so we typically look at it as a function of omega only over the range minus pi to pi, and then it's 2 pi periodic outside of that range. So we see that we have an infinite sum, and these are the terms that we'll be summing up. And if you remember from your Calc 2 days, anytime you have an infinite sum, the very first question you need to ask is, does this actually converge to something? So the mathematicians say if it converges to something, and in our case we want it to converge for every value of omega. So notice that for each value of omega, we have a different infinite sum that we have to sum up. So we're interested in this, asking the question, does this converge for every value of omega? And so if it does, then we say the DTFT exists. If there's at least one omega for which this doesn't converge, then we say that the DTFT of this signal doesn't exist. And there are many signals, many of which are actually of very practical interest, for which the DTFT technically does not exist. And so the Z-transform is introduced to allow us to handle those. And by simultaneously doing that, we simultaneously get the idea, as we'll mention later, we get the ability to be able to handle unstable systems. So if you remember, we talked about a stable system has an impulse response that is absolutely summable. And so if that stable, if we have an absolutely summable impulse response, its DTFT will exist. If it is not, so if it is unstable, then the DTFT of the impulse response, which would be the frequency response, does not exist. So the DTFT does not allow us to deal with certain types of input signals, but it also does not allow us to deal with unstable systems. So what do? Part of the reason, or the problem why this doesn't converge is, as I said up here, we're looking at these kinds of terms. So it's an interplay between what x of n is doing and what that e to the minus j omega n is doing. And if we look at these terms here, we see that they are complex numbers, but they have unit magnitude. So they, in and of themselves, really neither decay nor explode. So the behavior of the sum, whether it converges or not, is entirely dependent upon the value, or the behavior of x, whether x decays fast enough. When we go to the z transform, as you see down here, we are now taking x and multiplying it by z to the minus n, where z is just a complex variable. So z is complex valued. And so if we come back up here, we're looking at z to the minus n. And since z is a complex number anywhere on the plane, we can write it in polar form this way. And if we expand that out, we can see that we get an alpha to the minus n out in front. So we can actually control how that term decays by picking different values of alpha. So by moving to different regions of the z plane, that term will have different behavior as far as the decay goes. So coming back down to this summation down here, what that means is that for a given x, and let's say it's one for which the DTFT does not exist, so that would be our big reason for wanting to go to the z transform in general, although it's not the only reason that we go there. But let's say we have an x of n for which the DTFT does not exist. Well, we know by comparing these results for DTFT and z transform, that would mean that we can't pick any z value that has a unit magnitude. So in the z plane, if we were to look at this z transform on the unit circle, the z transform would not exist because this sum would not converge for the scenario that we've set up here. But there should be, or hopefully will be, other z values, regions on the z plane that will force the sum to converge, and then there will be some other z values besides just the unit circle that will cause this sum to not converge. So we can define this. Let me try to get rid of some of this stuff here. We can define this just fine, just like this. But what we need to do is say, well, this definition is only valid for values of z for which this summation converges. And we'll get into that in just a little bit when we talk about this thing called the region of convergence. In fact, it might even be on the very next slide. But I do want to, before we head off to the next slide, point out that we are talking about the two-sided version of the z transform. That means that we are summing from n equal minus infinity to infinity. There's a version of the z transform called the one-sided, and I tended to focus on that in the signals and systems class, but here I'm going to focus mostly on the two-sided. The one-sided z transform is nice when you're dealing with initial conditions, and therefore it's more widely used in control systems. The two-sided is a little more widely used in DSP, although there are some scenarios where we might want to consider the one-sided. So for the most part, they work very similarly. There's fewer differences than there are similarities between these, but you should be aware that there are two different flavors of the z transform. So So the Z transform, as we just saw, gives us a complex valued function on a complex plane. So remember, the DTFT gave us a complex valued function, capital X of omega, but omega was a real variable, so we could plot that on a single axis. But since the DTFT was complex valued, we needed a magnitude versus omega, and we needed a phase or an angle versus omega. But now we have, we compound that issue even more. We have a complex valued function, so we need to plot both magnitude and phase, but now we're plotting them over a plane. So we're plotting on the z plane, where one axis is the real part of z and the other axis is the imaginary part of z. So this is the plane that we're plotting it over, and the actual plot would be a surface above or below this plane. If we're plotting magnitude, it would entirely reside above the plane, since magnitude can't go negative. But if we were plotting phase over this plane, it could go positive or negative. But as I point out here, we mostly look at the magnitude plot of Z transforms. We rarely look at the phase plot. In fact, I can't ever really remember wanting to look at the phase plot of a Z transform. I'm not saying it doesn't happen, I'm just saying it's very, very unusual. As we were just talking about, this idea of certain values of z for which things converge and don't converge, it will be handy to break up our z plane into different regions. And I'm not saying that these are the regions of convergence. I'm just saying there are different regions that we like to be able to have a name for, or at least refer to. So we'll be dealing with the unit circle. So I say into two parts. Technically, I guess I should say three parts. We have the unit circle, and that's kind of the dividing border between these two regions. The other region is all the values of z inside the unit circle. So that's any complex z value whose magnitude is less than 1. And then the other region is all those values of z outside the unit circle. So those are all the z values on the z plane whose magnitude is bigger than 1. Okay, now we are going to get into this region of convergence, or ROC. So just making you recall here that the big motivation for going to the Z transform is that it allows us to handle or to get convergence for signals for which the DTFT sum does not converge. So we look at these two sums, and we again recognize that Z is just an arbitrary complex variable. And so we can write it as alpha with alpha greater than 0, e to the j omega. And so those are the two differences. So suppose, let's just talk for the moment that we have a signal, x of n, for which the DTFT does not converge. The Z transform hopefully will converge for some values of z, but maybe not for others. Now, for the case where we have a signal for which the DTFT does not converge, then clearly the Z transform can't converge for those values of z whose magnitude is equal to 1, because that would be on the unit circle, and that would be replacing z by e to the j omega, and we would end up getting the Z transform becomes the DTFT. So just remember, we talked about this in the signals and systems class. If we have the Z transform and we evaluate it on the unit circle, that the result is the DTFT. And if the original DTFT does not converge, then the Z transform itself can't converge on the unit circle. So if we have such a signal, our Z transform will not converge on the unit circle, but hopefully there will be other values of z for which the Z transform summation does converge. but sometimes there's none at all. But we're hoping that we're talking about a signal for which there is at least some set of z. Otherwise, the z transform will be a useless tool for us in that case. And at this point, we'd kind of be out of luck. We wouldn't be able to handle that. So we're going to define the region of convergence for a given signal. So you tell me what x of n is. I'm going to try to find its z transform x of z, but I also have to specify the region of convergence. So what values of z does this z transform sum actually converge to something that I can write down as an x of z? And I'm just pointing out here again that each signal has its own region of convergence. So it's not like there's just one and only one region of convergence. As you say, here's signal 1, here's its z transform, which is valid on this region of convergence. So that's the kind of scenario we're talking about. So best to illustrate this with an example, perhaps, let's look at our unit impulse sequence or our delta function. So if we plug that into our definition, here's the z transform of the delta function symbolically. We plug in the delta function into the summation, and now we think about what does that summation notation tell us? Well, we're just running from n equal to minus infinity up to infinity. But remember that for almost all the values of n, delta of n is equal to 0. So we've got an infinite number of zeros and an infinite number of zeros, and there's only one term when n is equal to 0 that delta of n is equal to 1. So there we have the 1 times z to the minus 0, which is just z to the 0. And remember, z to the 0 is just equal to 1. Anything to the 0 is equal to 1. And so we end up getting 0 plus 0 plus 0, dot, 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 plus 1 plus 0 plus 0 plus 0, dot, 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 dot. So all that adds up to be is 1. So we now have that the z transform of the delta function is nothing more than the number 1. So we can write that as delta of n transforms into 1. I mean, we have to be aware that our transform here is talking about the z transform, not some other transform. But we also have to specify the region of convergence. And we go back up here and we look at this sum, this infinite summation. That's where we need to look to see under what conditions does that infinite sum actually converge. Well, in this case, this infinite sum isn't really an infinite sum at all. There's only one term that's non-zero. So there's no convergence issue here at all. There is no value of z for which this does not converge. So the region of convergence for this result is all of z. Everywhere on the z plane, this result holds. And so on my Signals and Systems webpage, there's a z transform table. There should also be one in the textbook. I haven't really looked carefully, but it should be there. If I remember, I'll post something up to the web page specifically for this course. Okay, moving on to the next slide. We're going to explore some examples and try to extract some general principles by first hitting ourselves with some simple examples. So suppose we have a finite duration signal and we'd like to take its z transform. I'd like to illustrate here that in that case the region of convergence is very easy to find, as is the z transform itself. So if you see a finite duration signal, any finite duration signal, there's no need to go looking on a z transform table to find out what it is. You can write it down immediately. So here we have our notation that says this x of n is finite duration, so it's 0 prior to that first one and 0 after that last one. And we see the arrow under the first one telling us that that is the n equal to 0 location. So then n equal to 1 would be the 2, and the 5 is at the n equal to 2 case location, and so on and so on. So we now have an easy way to show where these things are, as we've seen before. So now, given that, we can substitute these numbers into this summation. So up until we hit n equal to 0, everything is 0. So we have this whole string of 0 times z to the 1, z to the 2, z to the 3, and so on. So remember, those are for negative n values, and we already have a negative sign out in front. So for n equal to negative 1, we get z to the 1. So that's why we have that. Then we finally hit this 1 at n equals 0, so we get this term. Then we have a 2 at n equal to 1, and so on, and so on, and so on, and so on. And then finally we hit all those after that are all zeros. So we have zeros evermore after that. All right, let me get rid of some of this stuff here. Okay, so once we do that, we get rid of all the things that have zeros in front of them. So we get rid of all of those, we get rid of all of those, and we get rid of that one. And all we have to do is write down everything that's left. So that's the functional form, and we now have to try to address under what conditions does that actually converge. So here it's not an issue of an infinite duration or an infinite summation that keeps getting bigger and bigger and bigger and doesn't converge. Here it's an issue of just, are there any z values for which the value of the z transform function that we've written down blows up? And so if we look at that, since we have all these z inverses here, anytime we were, if we tried to put in z equal to 0, we would, see that we have a problem, because we would end up with something in the form of 1 over 0 for each of those z inverse terms. So our region of convergence, well, let me back up. So any other value of z is fine. We just can't put in z equal to 0. So at z equal to 0, it's as if the summation explodes, and so our region of convergence will be the entire z-plane except z equal to 0. So that's one example. That was for a causal finite duration signal. If we now look at a finite duration signal that's kind of bidirectional, so it starts for n equal to 0 here at the arrow, and we have 3 terms in the positive n direction and 2 terms in the negative n direction. We play the same game. We substitute all these things into our summation, and we end up with something like this. Now, for this case, since it's going in both directions from n equal to 0, we get some positive exponents of z and we get some negative exponents of z. And so now we can look at this and say, well, all right, when z is equal to 0, these 2 terms will explode. And when z is equal to infinity, these 2 terms will explode. So we have to exclude those, but any other value of z, we don't get any explosion whatsoever. So we end up being able to say that we have a scenario here where we have this result that is valid on the entire z-plane except z equals 0 and z equal to infinity. So 2 simple examples kind of showing how we can determine the region of convergence for finite duration signals. Very good. Final example, well, no surprise, we've looked at one that was causal. We looked at one that was bidirectional. Now we'll look at one that we call anti-causal. So it's finite duration, but it doesn't go beyond n equal to 0. So again, we play the same trick, substitute the values in, and we get a functional form, and we now have to ask ourselves, are there any z values for which that functional form blows up? And we see that we have no z inverses, so it can't blow up at z equal to 0. But if z goes to infinity, then in fact we do have a problem. And so we say the entire z-plane except z equal to infinity. Now, just a word of comment here, a word of comment, okay? Just a comment here. If we, recall that z is a complex variable. So what does it mean that z is equal to infinity? Remember, we're thinking about a complex plane where we have, the real part of z and the imaginary part of z. Well, z equal to infinity you can think of as any point infinitely far from the origin. Doesn't matter what its angle is. So, kind of infinitely far off on the horizon in any direction. Okay, so summarizing these three results, and we just did this through example, but it's pretty straightforward to convince yourself that this would be true in general. So if we have a finite duration causal signal, the region of convergence will always be all of the z-plane except at the origin. If we have an anti-causal finite duration signal, we must exclude z equal to infinity. And if we have a bidirectional finite duration signal, then we must exclude both of those points. So very simple scenarios to remember, and you should keep those straight in your head. Pretty easy to kind of deduce them too, so you don't really have to truly memorize them. Okay, so that's the case for finite duration signals. Let's look at what we get for infinite duration signals, and things are a little bit harder here to analyze, but not terribly difficult. And what we'll do is, just like we did for the finite duration case, motivate with a simple example. So suppose we have the unit step function. So if you remember, that's zeros all the way up until we hit n equal to 1, where it jumps to 1 and then stays at 1 forevermore. So if we substitute in for our, well, first of all, once we plug in u of n here, our lower limit on our sum need not be below n equal to 0. Furthermore, once we've substituted in u of n there, and we've truncated the summation just for n equals 0 and higher, we can then substitute in 1 for the unit step. So we end up with, you can imagine, instead of having the u of n there, we've got a 1 there, since over this range, that's what the value of that thing takes on. So let me get rid of this here. Okay, so we end up with this summation, and I'm sure you studied at some point in Calc 2 or somewhere along the way, you heard something about a geometric sum or a geometric series or something like that. You can look this up in a book, or these days more likely on Google, and you'll find information on the geometric sum, and you'll see that you can rewrite the geometric sum in this form as long as the magnitude of z is greater than 1 for this particular form of this result. Notice that when the magnitude of z is greater than 1, since we're raising this to a negative power, that's the condition where the magnitude of these individual terms in the sum keeps getting smaller and smaller and smaller, and fast enough so that it will actually converge. So that's a general result that you should know. And so we get this result directly from the geometric sum result in the form that it's usually stated. And we look at that and say, well, I can simplify that. I see that z inverse there, and it's kind of bugging me. So let's get rid of that and get this into a function of z rather than a function of z inverse. So multiply top and bottom by z, and you end up with something that looks like this: z over z minus 1. And because of this, we're able to state what our region of convergence is. That's a part of the geometric sum result as to when does that sum converge to this functional form. So our region of convergence is all z whose magnitude is greater than 1. So this result converges for all z outside of the unit circle. So we can write down, here's our result, and you could write it either this form or this form. Either one is fine, but in both you need to write that the region of convergence is all z with magnitude of z greater than 1. Okay, so that's our first result for an infinite duration signal. Let's look at another example. Here we're going to look at a causal exponential. So we're using the u of n to enforce the causal part. Remember, we talk about causal systems, but we also talk about causal signals. Similar idea, but a little bit different. So a causal signal is just one that starts at n equal to 0 and then is 0 prior to that. And so the unit step here is there just to enforce that. So the real structure is a to the n. So this thing starts, well, it's 0 up until n equal to 0, and then from that point onward just follows this exponential behavior, doing whatever it is that a tells it to do. And whether it decays or explodes or oscillates and decays and oscillates and explodes will depend upon the nature of a, as we've discussed in an earlier set of notes. Okay, so say for example a were greater than 1 in magnitude, we would know that the DTFT of this signal would not converge because x of n itself is diverging. But let's take a look at what happens for the z transform. So we plug in our result. We don't need to put the u of n in there because we've already limited our sum from n equals 0 to infinity. Going here, we've just rewritten. We've taken the a to the n, and then we've interpreted z to the minus n as 1 over z to the n. And then we've combined the a and the 1 over z together, just using properties of exponents. And again, this is just an example of the geometric sum, and we can apply the geometric sum result to get this form under the constraint that a over z has a magnitude that's less than 1. So that just comes from the convergence characteristic of the geometric sum result. And then we can clear the z inverse and get something that looks like z over z minus a. And our region of convergence will be all z such that magnitude of z is greater than magnitude of a. So I'm just showing that here, this square actually goes out, forever. I just couldn't really easily show that. So the region of convergence is everything outside a circle with a radius of magnitude of a. And so I would encourage you to compare this result to the previous result with just the unit step, which we would get for a equal to 1, and you'll see that this result is actually just a generalization of the unit step result. So we've been sneaking up on this general idea for the region of convergence of a causal signal. We've seen 2 examples now where the region of convergence is the region outside of some circle. And we can show that that is true in general. So we've got our causal signal z transform. It's causal, so we can start at n equal to 0. And now we're going to substitute in general polar form for z just to get a feeling for what this thing's going to look like. So we give that a little look there, and we see, well, all right, the e to the minus j terms, they have unit magnitude. So regardless of the value of omega, they're really not doing much to make these terms get smaller. In fact, they're doing nothing to make the terms get smaller, really. So we should guess that the behavior of the convergence of this should depend on the alphas and not really on the omegas. So that angle should be irrelevant to the region of convergence and really should only depend upon how far from the origin is the z point. And we can actually show this mathematically. So if we start out with our x of z and look at its magnitude, so we apply the magnitude to the summation, and now we just use a version of this simple result, which you should be able to look at and say, yeah, that makes sense. Well, going from here to here is just that same result. Then we have the magnitude of the product of two things as the product of their two magnitudes. Then we use the fact that we can write z in terms of its polar form and break this down into these two things, where we recognize that that magnitude is just equal to 1, and so we can eliminate that. And so now we see that we get something that looks like this, where we've just for convenience taken the alpha to the minus n, put it down in the denominator as alpha to the n. And so now we see that the convergence of this really, I mean, the omega is gone. So this sum converges based upon an interplay between the behavior of the x values and the value of alpha. So it's basically a race between how does this go down and how does that go down. And so the whole point of this is that we've just established that to bound this, we must have this be, if this is bounded, then this is bounded. And we can see that that happens only as a dependence on alpha, not on omega. So what that tells us then is that for any causal signal, infinite duration, that the region of convergence is the region outside of a circle. And that's, we see this up here that the slower this decays, that means the harder it's making for the summation to actually converge, the faster we need this thing to decay. And so if we need 1 over alpha n to decay fast, that means we need to be farther out. And so we can deduce that this is the general form of the region of convergence for a causal infinite duration signal. And we can tie this back to the result that we saw for the causal finite duration signal. So r sub c here is just the radius of the circle for which this a particular z transform result converges. Or sets the region of convergence outside of that circle. And for the finite duration case, r sub c is just equal to 0. If you remember, we said everywhere except at the origin. So we would have a circle of radius 0 would give us just the origin to be excluded. We can do a similar kind of thing. I'll go through this a little bit faster because it's virtually the same idea. The only difference is that we have to play a game here where we flip the signs around, and now instead of the sum going from minus infinity to 0 goes from 0 to infinity. Once we get that, everything else ends up working exactly the same. But now instead of having 1 over alpha n, we have alpha to the n. So you would expect things to work reciprocally to what they were before. And now, same kind of reasoning, we can say that for an anti-causal, perfectly anti-causal infinite duration signal, the region of convergence is inside a circle of some radius r sub a. There should be an a subscript on that. So there is some r sub a that sets that, and any z inside that circle will also converge. And likewise, this is consistent with our anti-causal finite duration signal where r sub a was equal to infinity. So that just meant anywhere on the z-plane except the z's that are infinite. Okay, so we can now use those two results and say, well, we can get a general signal by decomposing it into a causal part and an anti-causal part, and those two would then get added together to create the general signal. And so it should end up being a union of these two types of region of convergence results. So one is the area outside a circle, and the other is the area inside a circle. So if the circle that we're looking at things inside is bigger than the circle for which we're looking at points outside, then we get something that looks like this, where the combined or the intersection of those two regions of convergence form a donut, or in more technical math terms, an annulus. So this is a general result that says a general infinite duration signal will have a region of convergence that is ring-shaped or annular region. Now there are scenarios where the R sub A, which is out here, and the R sub C here are such that R sub A is less than R sub C, in which case the intersection is zero. The two individual regions of convergence do not overlap, and so for such a signal, there is no region of convergence, and so then we would say that the Z transform does not exist anywhere. Okay, move on to the next slide and just summarize everything. So this is just a nice one-stop shopping for the results here. If we have a causal signal, we have a region of convergence that lies outside a circle. Anti-causal signal lies inside, and a bidirectional signal either is an annular region, a ring, or is nothing at all. Those are the cases that we can have. So let's finish this up, just connecting this back. We've alluded to connecting this back to the DTFT a couple times. And now that we have the region of convergence ideas, we can say, that remember, the connection between the Z transform and the DTFT is the following. If we look at the Z transform and we replace Z by e to the j omega, we get the DTFT. Well, notice that this replacement lies on the unit circle. So in order for that DTFT result to actually exist, Z's of this form must fall in the region of convergence. So what that says is, in order for us to go from Z transform to DTFT, the region of convergence must include the unit circle. And so here's an example for this case that we looked at earlier. The causal exponential function, we saw that we got this result as our Z transform. And since that is a causal signal, we saw that we got a result that said all Z outside the circle of radius A are in the region of convergence. And so if A is less than 1, then the region of convergence includes the unit circle, and the DTFT exists. And when the DTFT exists, all we have to do is take the Z and replace it by e to the j omega. When we do that, we get this result, and that matches exactly what we have seen earlier in our other course, is the DTFT of this decaying exponential. So so remember, when A has a magnitude less than 1, this signal that we started with is a decaying causal signal. So that means that as long as we have decaying sinusoids, we can deal with DTFTs. But as soon as we start getting into exploding exponentials, then the DTFT is a tool that fails to work, but the Z transform comes to our rescue. And we've also seen that the impulse response of systems have these exponential terms often, in fact almost always for the kinds of systems we're interested in. And these terms have to decay in order for the system to be stable. But if we're talking about an unstable system, they would grow without bound. So again, seeing the idea that the Z transform allows us to deal with the scenario of an unstable system, and that is one of the key motivations for using it. And then finally finishing off with one last view of this discrete time system relationships. So we've been talking about the difference equation and the block diagram in previous note sets, impulse response as well. We're now talking about the Z transform, and the main reason that we're going to be talking about or applying the Z transform is that it will allow us to get the impulse response. I'm sorry, the transfer function, and we can do that by inspection, and then we can also link that to the impulse response, and we can also link it to the pole zero diagram. And when the unit circle is in the region of convergence, then we can replace Z by e to the j omega, and we can get the frequency response of the system. So these are very important concepts and insights into how to navigate around a system as we're dealing with it. So that's all we have in this note set, and I will see you in the next note set.